Thanks. So thanks, Dick, very much for the introduction, and thanks everybody for coming, especially because I know that my talk is conflicting with the third presidential debate. So thank you for having all your priorities straight, I guess. Yeah. So I hope to be just as entertaining and informative as the debate is. Yeah. Maybe we can have just as substantive a policy discussion. Okay, yeah, and also thank you to the Simons Institute for inviting me to come. It's a real honor to get to speak in this lecture series, which has had many great speakers in the past, and it's a really cool series. And yeah, I'm just very, very thrilled to get the opportunity to talk to you all today about some research that really excites me. So what am I going to talk about today? I'm going to talk about something called error correcting codes. So in case you didn't get that, that's error, 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 correcting, 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 codes, codes, codes. Okay. So what is this talk actually about? All right, outline, outline, outline. This talk is about the question, how can we communicate in a noisy environment? Okay, so let's say that you have some message and you want to tell it to your friend. And for whatever reason, maybe you're in a noisy room, maybe there's a lot of, you're on a bad connection, something, your friend just can't hear you. Like, the message isn't getting through. What do you do? So one solution is to just, repeat your message again and again. And eventually, it'll probably get through. So for example, as in the title of this talk or the title of this slide, I really want to make sure that I'm clear, so I just repeated it a whole bunch of times. Actually, on that note, if I'm not clear, please do feel free to ask questions. We have the advantage of a two-way communication here, which in this talk we will not have. Anyway, okay, so we'd like to communicate, we can repeat things, and this actually, for humans, this works pretty well. Like if I just repeat my message again and again, eventually I'll get through, and what are the downsides? Maybe I look like an idiot repeating myself again and again, and maybe it takes me some time, it takes me extra time to talk again and again and again, but whatever, I'm an academic, right? My time is pretty cheap, so whatever. Okay, so for humans, this is a perfectly reasonable solution. But it turns out, if you think about it, for lots of other things that communicate, like your cell phone to a cell tower, or a satellite to a satellite dish, something like this, all of a sudden this overhead starts to become kind of bad. Right, so in these settings, we have these things that are communicating huge amounts of data in very noisy environments, right? These signals are traveling through space, maybe, like who knows what's happening to them. And we really expect these signals to be able to be transmitted reliably. Okay. So how is it the case that these things can transmit signals reliably without just repeating themselves? And it turns out, in this case, repeating yourself, if you're one of these systems, is extremely costly. It costs time, it costs power, and we don't want to do it. So what can we do? So these systems employ something called error correcting codes. And that's what this talk is about. So for the first part of the talk, I'm going to talk sort of define error correcting codes, talk about what they are and how they can be used to solve this problem in communication. It turns out there's actually lots of ways to solve this problem. There's lots of different types of error correcting codes. And unfortunately, I won't be able to talk about them all tonight, even though they're all super cool and exciting. So instead, I'm just going to focus in on one fundamental idea in coding theory. And this idea is at the heart of a family of codes called Reed-Solomon codes, which have been incredibly important over the past 60 years in communication, storage, and lots of other areas. And so this fundamental idea, okay, wait for it, 2 points determine a line. Okay, so that's it. So if I take 2 points in space, like on a plane, there's exactly one line that goes through them. So this might seem like, okay, that seems pretty obvious, maybe not entirely clear what the relationship is between that and communication. But it turns out that this idea is at the heart of lots of analyses and constructions of error correcting codes, these communication systems that have been used since the 60s. And it's extremely fundamental. So in the second part of this talk, I will sort of talk about this idea a little bit, talk about how we can generalize it, and talk about the mathematics of how this idea can be used to design communication systems, which are very powerful. Okay. And finally, in the third part of the talk, I'm going to sort of move up to the research frontier. So this idea and the codes that are derived from it have actually been around since the 60s, so they're pretty classical. But it turns out that there's lots of really exciting new research being done in coding theory and based on this idea in particular today. So in this last part of the talk, I want to focus in on a few modern directions. And once again, there are tons and tons of different research areas that are active now that are very exciting, and I won't have time to talk about them all. But I'm just going to pick one topic in computational biology and kind of tell you guys how these ideas in communication have been very useful recently in something seemingly unrelated to computational biology. Okay. So that's the idea of the talk. So we'll start out talking about error-correcting codes, what they are, how can they be used to solve this problem. Then we'll focus in on this one fundamental idea and see how that in particular can be used to solve this problem. And then we'll sort of dive ahead and see how it can be used to solve not just the problem of communication, but tons of other problems, all the other problems, basically. Okay, so that's the idea. All right, so I said that for humans, repeating ourselves is pretty much okay. It's these other systems that we care about where repeating ourselves becomes problematic. That said, when we talk about error-correcting codes, a lot of times we like to anthropomorphize things, and so we often think about it as humans communicating. So I'm going to set up the problem as sort of a toy problem between two characters named Alice and Bob. So Alice is a sender and Bob is a receiver. So Alice wants to send a message to Bob. And the problem is that they are communicating in a noisy environment, right? So why is this a problem? It's a problem because even just a little bit of noise can have big consequences. So let me illustrate this first by kind of a silly example, and then we'll get a little bit less silly. But here's a first example of how a little bit of noise can have big consequences. So suppose that Alice wants to talk to Bob, and Alice wants to talk to Bob about panda bears. Okay? And Alice and Bob both agree panda bears are large, adorable mammals, live in China, eat bamboo shoots and leaves. Right? So Alice says, eats shoots and leaves. Bob knows exactly what she's talking about. Panda bear eating plants. So far, so good. Okay. However, this is a problem, right? Turns out that the way that Alice has chosen to express herself here is not very robust in the presence of errors. Right? So for example, I could change this message just a little bit. If I go and introduce just a couple of changes, a couple of commas, yeah, all of a sudden this phrase means something slightly different, and Bob might get confused. Right? So instead of thinking about a panda bear who's eating plants, he's going to think about someone, maybe a panda bear, who eats as in a hamburger, shoots as in a gun, and leaves as in skedaddles. And this is not the message that Alice meant to say. This is terrible. Everything's gone wrong. Horrible miscommunication. Okay, so what can they do about this? So just like we were saying before, maybe Alice could choose a way to express herself that were a little less susceptible to this sort of error, right? So for example, she could just shout, "Panda eats plants," repeatedly, okay? And Bob would probably get the idea. But again, this has downsides. It has the downside that Alice looks kind of silly. It has the downside that she spends a lot of time communicating. And we want to know, is this really the best thing she could do to get her message across? Right? So the question we want to answer is, what is the best way to introduce this redundancy? Okay. And that's where error correcting codes come in. Okay, so that was my silly example. Let's step back from the silly example a little bit. Still with the cartoon pandas, though. They're going to be here for the rest of the talk. And try to figure out what exactly is going on. Let's try to formalize this problem a little bit so we can actually solve it. Okay, so what's going on? So in the previous example, Alice wanted to talk to Bob, and she wanted to send him one of two messages, right? Either she was going to say, "Hey, Bob, panda eats plants," or she was going to say, "Hey, Bob, watch out, panda's got a gun," right? And Bob's job was just to distinguish between these two messages. And the problem in the previous slide was that Bob could not distinguish between these two messages in the presence of noise. So more generally, we might imagine that Alice actually wants to send not just one of two messages, but maybe one of a whole host of panda-related messages, right? So maybe all of these things. Okay. So how are they going to do this? All right, so Alice and Bob, so again, they're being proxies for other sorts of communication devices. So being normal human beings who are proxies for other sorts of communication devices, Alice and Bob, of course, communicate in zeros and ones. All right, so a very natural way for them to try to solve this problem is to assign a string of zeros and ones to each of these possible messages. Okay, so I've got 8 messages here, and there are 8 strings of zeros and ones of length 3, and so I've assigned just one of these strings to each of these possible messages. And so if Alice wants to say panda eats plants, she's going to send Bob the panda eats plants string, so 0, 0, 0. Right? And Bob knows exactly what she's talking about. So this is the analog of the kind of not very good scheme that we saw before, the punny English sentence. Right? Because if even one bit gets flipped, Bob gets the wrong idea. So this solution is very fragile. And actually, this is even worse, because if I flip another bit, Bob gets a completely different idea. So this is really not very robust. So what can they do? Okay, so the first thing we would try is repetition. Right? So we might try, let's take these messages and just repeat them 3 times. So instead of 0, 0, 0, I'm going to have 0, 0, 0, 0, 0, 0, 0, 0, 0. Instead of 0, 0, 1, I'm going to have 0, 0, 1, 0, 0, 1, 0, 0, 1, and so on. And this actually works if Alice and Bob are only trying to protect against one bit getting flipped. Right? Because if Alice wants to say, "Hey, Bob, panda eats plants," she sends him this string of 3 copies of 0, 0, 0. And if one error occurs, Bob actually, he's pretty good. He can still figure out what Alice meant to say, right? Because there were 3 copies here, and only one of them got corrupted. So he can just look at this, and he can say, OK, the vote is 2 against 1 that Alice meant to say panda eats plants, so I'm going to go with that. And he'd be right in this case. So this works. This works great when there's only one error. The problem, as we've discussed before, is that I had to go to a really tiny font even to fit these strings below my cartoon pandas. Right? These are a lot of bits. There's a lot of communication. And we might ask, is there some middle ground between the 3-bit solution that was extremely brittle and the 9-bit solution that was actually pretty robust, at least to one error? And the answer turns out to be yes. And so here's another solution. So this solution uses 6 bits per message. Okay, so for each of these messages, I've assigned a string of 6 bits. And I've picked these strings very carefully. They have the property that any 2 of them differ in at least 3 places. So you can check me if you don't believe me, but I promise it's true. Any 2 of these strings differ in at least 3 places. So why is this good for Alice and Bob? Well, it means that if Alice wants to say panda eats plants, she'll send Bob the all-0 string. OK, so far so good. And now what happens if 1 bit gets flipped? So if 1 bit gets flipped, this string, well, it's 1 away from the string that Alice meant to send. And because they're all 3 apart, that means it's at least 2 away from all of the other strings. Okay, so what can Bob do? He can go and look at all of the possible strings that Alice might have sent, right, and say, what I heard is closest to this one. So I'm going to go with that. And in this case, if there's only going to be 1 error, Bob will be right. Right? Does that make sense? Cool. And so this works no matter what bit got flipped. Right? If a different bit got flipped, same argument holds. And it also works no matter what message Bob meant to say, or Alice meant to say. Right? So if Alice meant to say bat panda, for example, then she would send the bat panda string. And even if 1 bit got flipped, Bob would correctly interpret bat panda. So this is great. So this is an example of an error-correcting code. That is, an error-correcting code, for the purposes of this talk, is just a whole bunch of strings, which we call code words, that are all mutually far apart. Okay. And so now there's a whole bunch of trade-offs we could talk about in this space, right? How many sets of strings? How many strings do we have? This sort of talks about how many messages Alice could possibly send to Bob. How expressive is their conversation? Right? Another thing we care about is how far apart these are. So in the previous slide, all the code words differed on exactly 3 bits, or at least 3 bits, which meant that they could tolerate 1 error. And you can imagine if these things are further apart and differ on more bits, then Alice and Bob could tolerate more errors. So we also want that to be big. And finally, we want the length to be small. Right? The whole point is to reduce overhead, reduce the amount of stuff that Alice has to say, because this turns out to be really costly in applications. So these sort of 3 parameters that we're trading off between gives us a really rich space to explore. Okay, so error-correcting codes have actually been around for a long time. They were introduced in the late 40s, early 50s by the seminal work of Claude Shannon and Richard Hamming. So these guys were researchers at Bell Labs at the time, and they were really interested in sort of the fundamental mathematics of communication. If I expect so many errors or errors in this model, how much can I hope to communicate? At what rate can I hope to communicate? And they really sort of laid out the foundation of basically all of modern information theory and coding theory. And there are many big questions that they asked. The big questions are mostly about these trade-offs, right? So the one that's sort of relevant to this talk is this one that I was talking about before. What are the best trade-offs you can get between the definitions between big and far apart and the length of these strings, using the definition that an error-correcting code is a big set of strings that are all far apart. So we have all these trade-offs. Another question that we might ask that has been asked since is, this clicker doesn't work very well, how can we achieve these good trade-offs with efficient algorithms? Right? So in the previous slide, what method did Bob use to recover Alice's message? Well, he looked through all of those 8 strings, and he figured out which one was closest to what he heard. So this works great when there are 8 strings. But imagine that maybe there are actually something like 2 to the 2 to the 8 strings or more. What does Bob do then? He could look over them all, but it would take him a really long time. And so one question that we also ask in coding theory is how can we achieve these trade-offs, find these big sets of strings that are structured in a really nice way that allow Alice and Bob to take advantage of this computationally so that they can somehow, faster than just by looking at all the strings, Bob can figure out what Alice meant to say. So these are big questions in coding theory. And in general, they are still open. So we don't know the answers to these fully. These are huge open questions. That said, we do know a lot. And error-correcting codes have really evolved a lot since the 50s. And by now, they're used basically everywhere you look. So they're not just helpful for my silly story about Alice and Bob, the cartoon people. They're also useful basically anywhere you could imagine communication happening. So for example, between your cell phone and a cell tower, there's an error-correcting code there fixing that between satellites and satellite dishes. They're also really useful in storage. So far we've been talking just about communication, but you can imagine that the same principle applies to storage, right? I have some data, and I want to go put it somewhere, like on a disk, and then something bad might happen to it. Bits might degrade, disks degrade, things catch on fire, terrible stuff happens. Right? And we want to be able to protect ourselves against this. And so one way to do it is to take your data, treat that as a message, as a cartoon panda, find the code word associated with it, and then put that on your disk instead. So then it's robust against errors that might happen in storage. They're also used in things like barcodes and QR codes. So this is the QR code on the poster. It's an error-correcting code. And again, same principle holds, right? When your phone tries to read a QR code, maybe bits of it get occluded, bits of it get covered up, your phone doesn't read it quite right. You want it to be able to be robust to any errors that are introduced in the reading process. So that's an error-correcting code as well. Similarly, internet protocols use error-correcting codes anywhere you could think. RAM. Also, it's useful in areas that you might not think. So for example, in computer security, there's lots of protocols that are used, crypto systems, which are based on ideas from error-correcting codes. Similarly, it's really useful in algorithm design for image processing and computational biology, which you might not expect because those don't seem immediately related to communication. But at the end of this talk, we'll sort of explain at least how the computational biology connection goes. Okay, so error-correcting codes used all over the place. And unfortunately, today, we cannot talk about all of them. So today, instead, I'm going to focus on just one particular idea, one particular way to generate all of these far apart strings. That's really our goal, is how do we get all these strings that are so far apart? And this idea, like I said earlier, is that 2 points determine a line. So in order to explain exactly what that means and how it can help us create these big sets of strings, I need just one mathematical tool, which are polynomials. Okay, so I promise this is the most technical slide. That's it. So here are polynomials. Here's a couple of examples of polynomials. So for example, this polynomial y equals x squared minus 1. This is a degree 2 polynomial. So the 2 is this degree here. And it's associated with a graph like this. And how do we get this graph? Well, I called this x-axis the x-axis. I call this axis the y-axis. And if I take x equals 0, for example, and plug it into this equation, I get y equals 0 minus 1, which is minus 1. So I put a little point there. Right here at minus 1. And if I plug in, for example, x equals 1, I get 1 minus 1, y equals 0. So I put a little point at x equals 1, y equals 0. And if I do this for all the points, I get this nice curve here. Okay, so that's a polynomial. This one is also a polynomial. This is a degree 3 polynomial. So 3 is this just biggest power that shows up there. Okay, so polynomials. Okay, so the idea that I wanted to talk about was that 2 points determine a line. So another name for a line is a degree 1 polynomial, right? So if I have 2 points here, there is a unique degree 1 polynomial that I can draw through these 2 points. So here it is. So there's my 2 points, and in this case, here was my degree 1 polynomial, my line. And actually, this idea generalizes just a little bit. Excuse me. Yeah, so these 2 points are enough to determine a line, but they're actually not enough to determine a degree 2 polynomial. Right? So if I take these 2 points, there's actually tons of degree 2 polynomials that go through these 2 points. There's tons of parabolas that I could draw through them. So maybe Alice likes this purple one here, the guy, and Bob likes that green one there, and there's tons of other. We can all pick our favorite parabola that goes through these 2 points. So not determined. However, if I add a third point there, then it turns out that there is a unique parabola that goes through those 3 points. So to see this, you can either stare at the picture for a little bit and be like, yeah, I don't really see how to fit any other parabolas there. Another way to see it is just sort of by thinking of the degrees of freedom you have. So a quadratic polynomial has the form y equals ax squared plus bx plus c. So sort of three things that you get to control there. There's A, there's B, and there's C. So it's kind of like if you pick three things, then you've pinned down exactly what this degree 2 polynomial should be. And here I get to pick 3 points. That's like three things. So at least morally speaking, stuff kind of adds up. Okay, so 3 points determine a degree 2 polynomial. And more generally, k points determine a degree k minus 1 polynomial. So here's 6 points, I guess, and here's the unique degree 5 polynomial that goes through them. Okay, does this make sense? Cool. Okay, so the question you might have at this point is, yeah, all right, what's so great about this? This seems pretty clear. So this idea, of course, is very old. You know, the Greeks knew about polynomials. But the idea of using these for communication dates back to 1960 with Irving Reed and Gustav Solomon, so these guys. So they were researchers at Lincoln Labs at MIT, and they were thinking about communication and thinking about how they could design these coding schemes. This is 10 years after Shannon and Hamming. And they realized that they could use this idea to make codes. And these codes are called Reed-Solomon codes, named after these guys. Okay. So how do they work? So let me tell you how these guys can use this idea that 2 points determine a line in order to define a whole bunch of strings that are really far apart. Remember, that was our goal. So first, I need to make just a slight tweak on the model. So we agreed sort of at the beginning of the talk that normal human beings communicate in zeros and ones, and I'm going to relax this a little bit. So I'm going to say instead of communicating in zeros and ones, Alice and Bob are allowed to communicate in numbers 0, 1, 2, 3, 4. Okay, so maybe instead of sending a string like this, Alice would send a string like that, right? Just 0, 1, 2, 3, 4. And we'll see why this is useful later. Just one more note about modular arithmetic. So if Alice and Bob are only allowed to use 0, 1, 2, 3, 4, then 0, 1, 2, 3, 4 are let's just say these are the only numbers allowed in our universe from now on for the rest of the talk. So how do we enforce that? There's obviously way more numbers than 0, 1, 2, 3, 4. So we work mod 5. And what that means is I take all of these integers from negative infinity up to positive infinity, and I'm going to turn them into either a 0, a 1, a 2, or a 3, or a 4. So these ones, 0, 1, 2, 3, 4, I can just keep as they are. Those are good. And then going forward, I'm just going to wrap around. So 5, I'm going to call that to be the same as 0. 6 is the same as 1. 7 is the same as 2, and so on. And going the other direction, I'll just wrap around the other way. So negative 1 is the same as 4. Negative 2 is the same as 3. Negative 3 is the same as 2, and so on all the way back. Okay. All right, so now we've changed our model a little bit. Alice and Bob are allowed to communicate in 0, 1, 2, 3, 4. Good? Okay, so now let's see how this idea that degree k polynomial, k points determine a degree k minus 1 polynomial can be used to help Alice and Bob in this setting. So here's the idea. So we have all these messages here, these panda-related messages, and we're going to associate to each one of them a polynomial, let's say a quadratic polynomial, degree 2. Okay, so here they are. So I'll associate to panda eats plants. He gets this nice blue curve. Go blue panda gets this green curve. Right there. Okay. I'm a UMich alum. Sometimes it gets a holler, but I guess not now. Go blue. All right. Jedi panda will get this red curve. Bat panda gets the purple curve, and so on. Okay. So how many curves actually are there? Right. So I'm going to include all of the polynomials of the form ax squared plus bx plus c, where a, b, and c I am allowed to choose to be 0, 1, 2, 3, 4. So how many of these are there? Well, there's 3 things that I get to choose. I get to choose 5 different things for each. So that's 5 cubed equals 125 such polynomials. So we can imagine there are actually 125 messages here that are encoded by these polynomials. But I am not going to draw 125 pandas, so this is what we get. Okay. So all of the possible messages are associated to a polynomial. And now what happens? What does Alice do? So suppose she wants to say panda eats plants, and panda eats plants is associated with this nice polynomial here. So what Alice says is basically just the evaluations of this polynomial. Right? So she'll go and look at 0, and she'll say, at 0, the y value is 3, so her first thing she'll say is 3. And then she'll look at 1, and she'll say, at 1, the y value is 0, so she'll say 0. Then she'll look at 2, and she'll say, okay, at 2, the y value is negative 1. That's not allowed, but we'll come back to it. So she'll say negative 1. Then she'll say, okay, what is 3? Well, the y value at 3 is 0, so then she'll say a 0. And then she'll say, what's the y value at 4? Well, it's 3 again, so then she'll say 3. Okay. But we just agreed negative 1 is not allowed, so she'll change that into a 4, because -1 is equal to 4 mod 5. Okay, so now that's what Alice will say. That's what she's going to send to Bob. And this gives us a mapping, sort of a correspondence between all of the messages and all of these strings. Okay. So it looks like this. So we have all of these messages, 125 different messages, associated with 125 different strings. And when Alice wants to talk to Bob and say, panda eats plants, she's going to send this string associated with panda eats plants. Okay. So why is this a good idea? So the whole point of an error-correcting code is that I have lots of strings that are really far apart. So I've certainly got lots of strings. I've got more strings than cartoon pandas that I want to draw, which is my definition of big. But now we need to show, are they actually far apart? And I claim that they are. I claim that these strings have exactly the same property as those strings we saw at the beginning of the talk, that any two of these differ in at least 3 places. Okay, so let's see why that's true. So imagine that Alice wants to send one message, and it looks like this parabola here. And if she wanted to send another message, say Jedi Panda, she would send this parabola here. And what I need to show to convince you that these are really far apart is that no matter what 2 polynomials she ends up choosing, these things must disagree in at least 3 places. So let's put them on top of each other. So I claim that they can only agree in 2 places. And the reason is because 3 points determine a degree 2 polynomial. Right? If they agreed in 3 places, they would have to be the same polynomial. And we decided at the beginning that they were different. Okay, so that means that they must only agree in 2 places. But there's only 5 places to begin with. Right? So if I only agree in 2 places, those 2, there must be 3 places, this one, and this one, in which they disagree. Okay, so that's it. That's the entire argument. And really the only fact we used is that 3 points determine a quadratic polynomial. Okay, so now I've proven this claim. Any 2 of these differ in at least 3 places, and that means that Alice and Bob can use these to communicate just like they could at the beginning of the talk. If Alice wants to say panda eats plants, she sends 30403. And if now it's not a bit, but if a symbol gets changed, so before we could only have 0 to 1 and 1 to 0, but now we can have anything, it can get changed to anything else. So if that 0 there got changed into a 2, what Bob sees is still closer to the panda eats plant string than it is to any of these other things. So now we've actually made substantial progress over our beginning slide. Right now I have 125 different messages. It's pretty cool. And so these are called Reed-Solomon codes. And more generally, I can think about polynomials of larger degree than quadratic, and I can think about letting Alice and Bob use numbers bigger than 1, 2, 3, 4, or 0, 1, 2, 3, 4. In general, they could actually go up to 0, 1, 2, 3, dot, 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 up to p minus 1, where p is a prime. And then this scheme will still work. And these are called Reed-Solomon codes. And Reed-Solomon codes, it turns out, show up all over the place. And so one of the reasons is that they have this really nice relationship between distance and length. They actually achieve the optimal relationship sort of for this parameter regime. Another reason goes back to this efficiency thing that I was talking about. They're really nicely structured. Right? There's lots of algebraic structure there because they're based on polynomials like this. And what that means is that when Bob is trying to figure out what Alice meant to say, he doesn't actually have to look over all possible polynomials. Instead, he just looks at what he gets, which is some points. And all he has to do is kind of figure out which is the polynomial that is closest to these points. And it turns out that that's something that he can do efficiently, just using algebra. He doesn't have to exhaustively search over all possibilities. So for these reasons, Reed-Solomon codes have become very popular. So actually, when they were first introduced in 1960, I think they were kind of regarded more as a mathematical curiosity than anything feasible. And the actual first real algorithms for them weren't developed until the mid-60s, and then the really fast algorithms for them weren't developed until the 70s. But by the late 70s, they really sort of took off. And since then, they are used in tons of applications. Yes, question?
Yeah. If algorithms are used in order to reconstruct the original polynomial, then don't the modulus values introduce additional error in capabilities, where if you have those incorrect values, then that should be considered an error because it's probably not going to yield the correct y-axis value that you would expect, right?
Right, yeah, so this is a very good point. So the question is, well, I was talking about polynomials, and I've been waving my hands as though this is a real valued polynomial. And when I loop things around, isn't that introducing more errors? And it turns out, via the magic of algebra, that as long as I loop things around with a prime modulus, it actually works out okay. So this is not at all obvious, but it turns out to work. If I tried to loop things around with a modulus that wasn't a prime, then you're right, that would actually cause problems. But yeah, this is one of the great facts of algebra, is that if you work modulo a prime, a lot of the things that you expect to be true over the reals, in fact, are still true over these things. They're called finite fields. And actually, more generally, this works over any finite fields, not just ones of prime order, but ones of prime power order as well. Yeah, so great question, thanks. Are there any other questions at this point? Awesome. Okay, so Reed-Solomon code. So where have we seen these before? So I claim that you actually encounter these things every day. In fact, many of the applications that we saw before use Reed-Solomon codes. So CDs, DVDs, Blu-ray, all of these use Reed-Solomon codes in their error correction. Barcodes and QR codes use Reed-Solomon codes. So this is the picture on the poster for this talk. So this is my face and a QR code. And so this is a really cool, it's a website called QArt. You should go take a look at it. But basically what this is doing is it's searching over all of the possible polynomials that could possibly encode the website for the Simons Institute, which is where this QR code links, and it finds one that just happens to look like my face. Which is really cool, right? That's a legit polynomial there. Those zeros, or like those pixels are encoding a polynomial that happens to look like my face. I find that really cool. So they're used in these codes. They're used in storage. RAID 6, which is a storage thing for doing distributed storage among several hard drives, uses Reed-Solomon codes. It's actually also used in data centers. So Facebook's data center uses Reed-Solomon codes for error correction. They're used in DSL. They were used in the Voyager probe, the spacecraft. So all those cool pictures that you've seen coming back from Uranus or whatever, those were all Reed-Solomon encoded to make it through space. So all using polynomials, using this idea that 2 points determine a line. They're also used in cryptography. So basically the idea behind Reed-Solomon codes, this sort of idea of using polynomials, is also really helpful in something called secure multipolarity computation, which lets people try to compute things jointly when they don't want anyone else to know their secret data. So this is also very useful in crypto. And it turns out to be useful in actually all sorts of areas of algorithm design for image processing, computational biology, and other areas like that. Okay. Whoops. Okay, so Reed-Solomon codes. I said this idea has been around since the 60s, and Reed-Solomon codes have been used in practice since sort of the late 70s, early 80s. So surely everything there is to know about these things are known, right? So what is there still to do? And actually, I think that working in coding theory today, even working on classical things like polynomials and Reed-Solomon codes, is a really exciting area of research for a number of reasons. So one thing that's super exciting is that there's lots of new application areas for these codes, which are raising new questions about them. Right? So one really good example is distributed storage. So in modern storage centers, you have all of these different nodes, and you have some data, and you want to distribute this data to all these different nodes. And sort of the model that we're working with for these data centers is that you have a lot of cheap computers, and they fail a lot of the time. So you want to use some sort of encoding to protect your data in case your servers fail. So this makes very natural sense for why you'd want to use an error correcting code. But if you think about it, sort of the model here is really different, mathematically speaking, from the model we were talking about at the beginning, where I'm sending some radio wave through space, and I'm expecting a whole lot of things to get corrupted, and I don't know which ones were corrupted, and there's lots. Here it's just like one server fails at a time. I know which one because it's the one that's down. Okay. And it turns out that this creates a really different parameter regime, really different questions. And there's all sorts of exciting research going on nowadays for how do we best use these codes, or how can we best modify these codes for use in distributed storage in data centers. And there's actually a lot of really cool work here at Berkeley being done in this particular area. So that's one example of modern research in error correcting codes, which is driven by modern technology, new questions. Another area of research is old questions. So it turns out there's lots of old hard questions which are still open. For example, the geometry of Reed-Solomon codes is one of them that I really like to think about. So you can think about these questions in coding theory as kind of a geometry problem. So here, this big green oval here, this is my artistic rendition of all of the strings of length 5, right? It looks just like it, right? Yeah. Okay. And there in the middle, I've highlighted these red dots are supposed to be the special ones that correspond to cartoon pandas, the ones that correspond to messages. And what we talked about before is this kind of almost geometric property, right, that any two of these things differed in at least 3 places. Okay, so if in my little cartoon here, I could say that all of these dots are at least 3 apart pairwise. Okay. But we might ask other geometry questions about this. We might ask, well, how are these dots kind of distributed in this space? Are there spaces, are there points where there's big holes, where there's not too many dots? Are there places where there's tons of dots kind of clustered together, or clustered as tightly together as they could be, conditional on all having distance 3? And it turns out that for a lot of these questions, we don't know the answer. Because unfortunately, it's not as simple as drawing a big green dot and putting a big green oval and putting a whole lot of red dots in it and saying we understand what it looks like. In reality, this geometry problem, it's really high dimensional. And the geometry that you're thinking about, it's not really sort of Euclidean geometry like we think about in 3 space, because this distance is some sort of discrete notion of distance. And so there's a lot of really beautiful math questions that arise from this that are super interesting, that we still don't know the answer to. So that's another area of active research. And finally, a third area of active research in coding theory and error-correcting codes is thinking about how we can apply these codes in a wider and wider and wider range of applications. So we started out talking about just communication. Hopefully I've convinced you they're maybe also useful in storage as well. But it turns out that they pop up all over the place, not just where you might think, like communication and storage. So I mentioned a couple examples about computer security. They're really useful in image processing, signal processing. And today I'm going to talk about how they're useful in computational biology. Right, so these Reed-Solomon codes, useful all over the place. Unfortunately, I don't have time now to talk about everything. So I'm going to spend sort of the last 15 minutes or so of this talk just focusing in on one particular example about computational biology. So before I move on, are there any questions about the setup, what these things are, the mathematics behind them? Okay, onwards. Right, so let's see an example of how this can be used in something that on the surface has nothing to do with communication. Okay, so I'm going to talk about a problem called combinatorial group testing, which has shown up recently in computational biology. Okay, so here's the group testing problem. Right, so actually I was trying to decide what should I talk to you about, right, for a specific application for sort of a modern topic, and there's so many good topics. And I really wanted to pick something that had some good theory. I wanted to pick something that was actually relevant in practice. And most importantly, I wanted to pick something that I could explain in 20 minutes using only cartoon pandas. And so this actually narrowed it down significantly less than you might think, but here I've converged on this computational biology application with my cartoon pandas. Okay, so here I have 7 pandas. And it's important to note that now these are representing actual pandas. They are not representing messages. Yeah. This is an important distinction because actual pandas can get sick. Okay, so let's say that some of these pandas are sick, but they're asymptomatic. We don't know which ones are sick. And we would like to learn which ones are sick. So what can we do? Well, one thing we can do is test them. We take a blood sample from every panda, run some science test, that's a beaker for science, right, and figure out which ones are positive, which ones are negative. And let's suppose we're living in kind of this ideal world where we don't have any false positives, we don't have any false negatives, everything's just perfect, nice, clean data. This is obviously not the case in the real world, but for now, let's imagine that. Okay. So I see that some pandas tested positive, some pandas tested negative, and I correctly conclude which ones tested positive. Okay. So this is great, except you could imagine if these tests are kind of costly, maybe we don't want to do this. Testing everybody might be very expensive. We might want to ask, can we do better? So to motivate this a little bit, let me tell you the original application of combinatorial group testing, which surprisingly was not testing cartoon pandas for a mysterious illness. Actually, it first arose in World War II, where the army wanted to test soldiers for syphilis. So it turns out some soldiers had syphilis, not too many. And at the time, syphilis tests were extremely expensive. And so the army just didn't have the resources to individually test every soldier for syphilis. So the idea that they came up with was to start pooling blood samples. And so it turns out if you pooled the blood samples of different soldiers, if you kind of assumed that not too many of them were sick, you could get away with using many fewer blood samples. So let's see how this works with our cartoon panda thing. Let's suppose, just for a minute, that there's only one sick panda. How would we figure out, with fewer than 7 tests, which one it was? Okay. So again, the key is to pool blood samples. So here's a pooling design. Oh, you can't really tell. These arrows are supposed to be red, and those ones are supposed to be yellow, but they kind of all show up the same. But in any case, here's a way to pool blood samples, and I claim that this will do the job. Right? So, for example, suppose that I do this, and I run my tests, and I find out that this one comes out positive, this one comes out negative, and this one comes out positive also. All right. Which panda was sick? Any guesses? Bat panda was sick. Right? And the way we can tell bat panda was sick was because he was the only one who participated in these 2 tests. Right? If I assume that there's only one panda who's sick, it must be this guy, because every other guy participates in some different sequence of tests. Right? And this works, so it's bat panda. So this works no matter what sequence I got. So for example, if I saw all 3 of these showing up, I would assume that private eye panda was the sick one, because he's the only one who participates in all 3 tests. So this is an example of how, by doing pooling, we can reduce the number of tests we need from 7 to 3. So that's pretty good. Okay, so that's what happens if one panda is sick. More generally, we might ask, what happens if many pandas are sick, multiple ones? What can we do? So we still want to pool blood samples. Right? So the game is the same. We have some sick pandas. We don't know which ones are sick. And we're allowed to pool samples. So we could take blood from this panda and blood from this panda, mix it together, and we get positive, because there was at least one sick panda in the pool. Similarly, if we took blood from these 2 pandas, we'd still get positive. We wouldn't get any information about how many pandas were sick. We'd just get the one bit of information, positive. On the other hand, if we saw this scheme, or this set, it would come out negative, because neither of those pandas were sick. Okay, so the rules are clear? Okay. So then the question is, all right, so if I'm allowed to pool blood samples, and I know that there are k sick pandas, how many tests do I need? Right? How few tests can I get away with in order to identify the k sick pandas? Okay. So it turns out, once again, I guess this is the theme of this talk. Actually, this question is still open, too. We don't know precisely the answer. But we do have some pretty good schemes. And some of the best schemes are based on error-correcting codes, and in fact, based on Reed-Solomon codes. So let's see how those work. So what is the connection between this and coding theory? OK, so here's all my pandas. They're still real-life pandas who might get sick, but now I'm going to identify them with the message pandas that were in the previous part of the talk, and I'm going to identify each of those with one of these Reed-Solomon code words that we came up with before. So here's this Reed-Solomon code that we had before. So to each panda, I'm going to associate a string of length 5 with numbers 0, 1, 2, 3, 4. And just to remind you, the key of these strings was that any 2 of them differed in at least 3 places. And moreover, we actually had 125 of them. Right? So I'm not going to draw all those pandas, but there are 125 pandas now, some of whom might be sick. Okay, so how does this scheme work? How can we use Reed-Solomon codes to identify the sick pandas? Right, so here's the solution. Here's a pooling design. So I'm going to tell you how to distribute this panda's blood into 25 possible pools. Okay, so this means that we had 125 pandas. Let's assume 2 of them are sick. I'm going to show you how to get away with only 25 tests instead of 125. So this is pretty good. Okay, so what do? So I'm going to take this panda. Let's say that this is his Reed-Solomon code word, 31213. I'm going to write that up on the top here of this grid. And then I'm going to distribute his blood according to these numbers, like that. So in this column, I'm going to put this panda's blood into into bucket number 3, because there's a 3 here. In this column, I'm going to put his blood into bucket number 1, because there's a 1 here, and so on, all the way across. Okay? And I claim that this works. So why does this work? So let's suppose that this panda is healthy, and that the 2 other sick pandas are some other pandas who are sick. So now what happens? Where does the actual blood that would test positive go? Well, remember, any of these strings differ in at least 3 places. So that means that they can agree in at most 2 places. So let's say that go blue panda's string agrees with panda has a gun string in, say, the first two places, 3, 1, and then these things which do not agree with this guy's. Right? So that means that this panda's positive blood would show up in these two pools, but in none of these 3 pools. And now we'll do it again with Jedi Panda. Let's say, in the worst case, Jedi Panda agrees with this guy in 2 other positions that weren't already taken by this one. So let's say he agrees in the 2 and the 1, but these other 3 must be different. So then his sick blood shows up in this pool and this pool, but not in the other 3. And the key point here is that this leaves one possible pool uncovered. Right? So there's one guy uncovered. It has no positive blood in it, so it's going to come up negative. And this means that I observed that this panda's blood went into this test, and this test came up negative. So it must be that this panda is healthy. So I can certify that this panda is healthy. And actually, this works for any of the pandas. So all the healthy pandas, I can certify their health by just saying, OK, look, there was a pool where they didn't come up, which didn't come out positive, so they must be healthy. And the 2 sick pandas are precisely those pandas for whom all of their tests came up positive. So here's a solution. And it turns out this is actually one of the best solutions we know to this problem in general, pooling. And it's been used a lot. So just to put this in a little bit of context, let me give you sort of a brief history of group testing. So like I mentioned, group testing was sort of introduced in the 40s in World War II by Dorfman for precisely this problem of figuring out which soldiers had syphilis. Okay. And then some time passed. And then in the 60s, Reed and Solomon did their work and invented Reed-Solomon codes, which is what we just saw. And in a few years later, in 1964, Couch and Singleton came up with this idea of using Reed-Solomon codes, using error-correcting codes to solve the group testing problem. Okay, so this is all still very old work, very classical. What's going on since then? Well, since then, the path kind of diverged a little bit. So in this top path, this is sort of the theory path. And so you can think this question, how many tests do you need to decide which K pandas are sick? This is a really nice math question. It's got some great combinatorics. So mathematicians basically went crazy, right, for like 50 years. It's proving all sorts of things, trying to prove lower bounds. Like I said, it's still open, but there's been a lot of really beautiful work in combinatorics trying to close these gaps. Computer scientists work really hard to find very fast algorithms to do this. So the algorithm that I described in the previous slide was, we'll just kind of look at every panda and see whether or not all their tests came up positive. That's pretty efficient, but you can actually do much more efficient than that. You can actually just look at all the tests and not have to look at every panda, just look at all the tests and be like, oh, it's bat panda's the one. This actually allows you to have sublinear time algorithms, so really fast algorithms. And also really nice constructions that are very structured and very explicit. Okay. So tons of really cool theory work has been done. On the other end of things, this is sort of the practice side. Syphilis tests became cheap eventually. People stopped using this to test soldiers for syphilis because we don't care so much anymore. But then this idea resurfaced in the 90s in computational biology for high-throughput screening. Right? So instead of soldiers, you have civilians, and instead of blood samples, you now have DNA samples. And you want to run some sort of genetic tests on these samples. And these tests are very costly. And so in the 90s, computational biologists started realizing that they could pool blood samples and make much better use of their resources. So they started doing this, and on their own, like as a community, they sort of investigated these pooling designs, which ones were best, which ones worked better than others. And in 2006, Nicolas Thierry-Meg introduced something called the shifted transversal design, or unfortunately, STD. Whatever, different communities. But these designs were really, really nice. They had all sorts of beautiful combinatorial properties. They worked really nice in practice with the types of pooling, the biology technology that people were using, like the robots which do pooling and stuff. These worked. They were very, very structured. They worked very well. And people started using them. So they started using them precisely for this DNA screening application. So this is a picture of a robot that does this pooling. So it goes and it shoots up DNA samples, and it goes and pools them down in a plate, and it does this repeatedly. Okay? So people started using this. It turns out this is also useful for genome sequencing, de novo genome sequencing. So basically, this is a little more complicated to see why this works. But basically, the idea is you want to sequence some genome. It's very expensive. One thing you can do is chunk up the genome into chunks, and then you pool these chunks. And what you get out are little pieces of information called reads, and you want to somehow assign reads to belong to certain chunks. And the way these chunks are chosen to be overlapping, it can be the case that not too many chunks are responsible for any particular read. And once again, you get this group testing problem. You want to know which chunks were responsible for the read, and then you can use this to help assemble the genome again. OK, so this is all very exciting. And one thing that I think is extremely exciting is that now all of a sudden these communities have started to come back together. So this is a great story that I love to tell. So I was once at a workshop in 2013 at the IMA in Minnesota. And this workshop was organized to bring together these two communities. So the organizers had realized that there were these two different communities, computational biologists and theoretical computer scientists, who had been thinking about this problem in parallel for a really long time. And hey, gosh, maybe it would be good to get us all in a room for a week. And so they did that. And what we discovered there, so basically, Nicolas Thierry-Meg was giving his talk about shifted transversal designs, and a coding theorist, Achi Rudra, stood up in the back of the room and said, "You've invented Reed-Solomon codes." And in fact, he was right. So shifted transversal designs are just Reed-Solomon codes. The computational biologists had discovered them on their own, which I think really speaks to the sort of the fundamental nature of these polynomials. And this actually led to a lot of really cool collaborations. So going both ways. So from the computational biology side, there's all sorts of these new problems and new settings that the theorists hadn't been thinking about because often theory la la land, maybe you haven't thought about it. And then from the other side, there's ways to use these really fast algorithms and explicit constructions in practice. So one particular example in this pooling for genome sequencing, this is a setting that's it's a little different than sort of the standard, you've got k sick pandas and you want to figure out which ones are sick. It's just there's a slight tweak on it. And so it turns out that using ideas from the theory community, they were able to import some really fast algorithms to do this and really speed up their process. And going the other way, it gave some new models for the theory community to think about, which is really exciting. Another great example of just how theory and practice can talk to each other. So the computational biologists had discovered Reed-Solomon codes, but they'd only discovered it over prime fields. So before, we were talking about all the numbers in the world are 0, 1, 2, 3, 4. And I mentioned that actually we could generalize this. All the numbers in the world are 0, 1, 2, 3, 4, up to p minus 1, where p is a prime, because that's what makes the arithmetic work out to answer your question. But it turns out even more generally, there's something called a finite field over which these schemes work. And finite fields come in two flavors. They come in flavors prime-sized and power of prime-sized. And the power of prime-sized, by which I mean like 3 cubed is the power of a prime, whereas 3 is a prime, right? So power of prime-sized fields are much less intuitive to think about. You can't just think about modular arithmetic like this. They actually require a little algebra. And so the computational biologists hadn't figured those out yet, because why would you if you don't have a background in algebra? But it turns out that the biology equipment they were using, it's sort of standard issue, can't be changed, comes in certain sizes. Like the plates that they pool things in have 96 wells. So it's an industry standard, can't be changed. And it turns out if you want to work with things that are prime-sized, this is kind of obnoxious. Like when you're designing these pooling schemes, what you would really like to be able to do is use an alphabet of size 16. So Alice and Bob are allowed to use 16 different characters. But if you're restricting yourself to a prime, well, you can use 13 or you can use 17. And these didn't really play nicely with the biology equipment that they were using. But sort of as soon as we had this conversation, they were like, oh, 16 is the power of a prime. We can do that too. And all of a sudden, they were able to much better utilize the resources, which I think is a cool story. Anyway, so this is just one example of the many different ways that Reed-Solomon codes show up in current research in areas that you might not even think of, like as being anything related to communication. Sick pandas, who knows? So Reed-Solomon codes are all over the place. Here's one example. And I just want to sort of conclude with some of the punchlines of the talk. So what did we talk about? So the main takeaways should be 2 points determine a line. Repeating yourself is not the best way to communicate. And in fact, both of these have implications far beyond communication. For example, to computational biology, but also to lots of other areas. Okay. So with that, I'll finish talking and take any questions that you have. So thanks so much. Yeah.
With the group testing, I was wondering, how do these schemes take into account that the test is sometimes wrong?
Right, yeah, so that's a very important thing that, yeah, so I was saying these arrows went both ways, right? So one thing that we learned when talking to the computational biologists is that our models of errors were not exactly accurate. Yeah, so there's several things you can do. So one thing is you can model the errors either as worst case errors, or you can model them as random errors, and then you do need to change the schemes a little bit to be robust to that. But yeah, you're absolutely right, that's an important consideration. Any other questions? Yeah.
Pooling design you described for blood testing seems to have kind of a similarity of some kind to compressed sensing.
Right.
Because it sort of relies on the fact that there's a small fraction of people that are positive in order for it to work. Is there a formal connection of some kind? Or?
So there's like a very close connection. So, so the question is, what is the relationship between this and compressed sensing? So in compressed sensing, it's very similar. So in compressed sensing, you have this big long matrix and a sparse vector, right? And you see the output of this matrix vector multiplication, and your goal is to recover the big sparse vector. And you can think about group testing here as actually having a very similar framework, semantically speaking. You have a big binary matrix, which represents your pooling design, and you're multiplying it by a sparse vector. But now the multiplication is over a Boolean algebra instead of over the real instead of over the real numbers. And this is sort of taking into account the fact that even if two sick pandas participate in the same pool, you only get one bit of information. You don't get the answer 2, you get the answer yes. Okay, so it's basically the same problem, except instead of having plus, you have or. Instead of having times, you have and. So that said, the mathematics actually turns out to be slightly different in terms of the sorts of guarantees you can get. So I guess asymptotically speaking, if you want to recover a k-sparse vector using compressed sensing, you need about k log n measurements. For group testing, it turns out you need about k squared log n measurements. And the extra squared is coming precisely from this difference in the algebraic model. But yeah, you're right, they're extremely closely connected. And actually, ideas from group testing and compressed sensing and coding theory actually have really intermingled. That's a very exciting area of research. Any other questions? Yeah.
Where'd you get the pandas?
I drew the pandas. No. Yeah, but before I was a computer scientist, I was once thought I might be a studio art major. Then I changed my mind. Yeah.
I was trying to think if there is any difference if the panda moves at very high speeds, like at the speed of light, which is impossible. Because the calculation changes, because there is a deformation of space and time.
For error correcting codes or for group testing? Yeah, so the answer is...
Is there anybody that's working to this thing?
I'm not sure. Yeah, I don't know. Yeah.
Trying to go to Mars and to go.
Yeah, I mean, so people do use, optical networks to communicate sometimes, which really does go at the speed of light, because that's what it is. I'm not sure if, yeah, actually, I don't know the answer to your question. It's an interesting question. Yeah.
I was under the impression that when satellites excuse me, are communicating photographs over these huge distances. Oh, so I got the impression they're just using repetition and not using some error-correcting codes. Am I wrong, or how do they communicate these photographs?
So there might be some satellites that are using repetition, but definitely many use error-correcting codes. So for example, Voyager uses Reed-Solomon codes. Most satellites, from which you get satellite TV, use something called turbo codes or LDPC codes. So most of them do use some sort of error correction.
But these would be Reed-Solomon codes with a sort of very high P. If you're doing modulo a prime.
Ah, that's right. Well, right. So the question is, how do you turn these Reed-Solomon codes, which are over numbers 0 through p-1 into bits, or just something that you can send. So the way that people get around that is something called concatenated codes. So basically, I'll take a Reed-Solomon code, and then I'll look at each symbol. And so the symbol is in numbers 0 through p, and I'll associate to each symbol. I'll actually encode that with a binary code. So I'll treat that symbol as a little vector of zeros and ones, and that's actually what gets sent.
Okay.
Yeah, exactly.
Thank you.
Any other questions? Yeah.
We know that humans can do a certain amount of error correction, so that if you look at a noisy image without using any polynomial algebra, you can sort of, well, in your example, we could possibly have figured out that that was you without doing any algebraic decoding.
Right.
Are there any ways to mix the power of algebra with the power of human perception to communicate?
That's a really good question. Well, so two answers. So the first answer is that one thing that's going on there is not so much that, or it is that we are, as humans, are doing error correction, but it's also that our ways of conveying things have redundancy built in, right? So like images are extremely redundant in the sense that we can compress them a lot, right? And for example, garbled speech is also, you can figure out what I mean to say even if I'm just kind of muttering. And the reason is that English has a lot of redundancy built in, as well as your own brain's error correction capabilities. But the second question then, yeah, that's really interesting. So could we somehow mix human computation with algebraic computation? It might be that you could imagine coming up with schemes with more efficient decoding algorithms using biology-inspired decoding methods. But yeah, I don't know. That's a really good idea. Yeah. Okay. All right. Yeah, I'll figure it out in the next whatever, and we'll see what happens. Yeah. Oh. Yeah.
Sorry. I just wanted to respond to.
Oh, great.
A little bit because, like, I know that neural networks, Hopfield networks in particular, they do have. You can sort of implement like an error correcting scheme. I'm not sure like how efficient it is compared to like we saw on codes, but they do have the same properties that like nearby representations get mapped to the correct message because because of the convergence of Hopfield networks, a type of neural network. So that is there is a connection there.
Oh, cool. Thanks. Yeah.
The question from the gentleman behind about the satellite transmission. There you have a limited amount of power of energy.
True.
And then you're doing a scanning, which is a line, and then you want to go as far as possible. So in this code, you get more bits and you get computational power. So in terms of using energy, nobody's looking at the energy that you are using to get the reliability. But it may be a price on this.
I mean, so people.
It's not free, I have to use more energy, so I don't know if a bit has energy in itself. But maybe.
Right. Yeah. So energy is an important consideration that people take into account. So certainly, if you're sending fewer bits, you're using less energy to transmit. But I think what you're talking about is then the computational cost for encoding that also incurs an energy cost, and definitely when people design these designs, especially for things like satellites, which have to work on wanting to conserve energy as much as possible. Yeah, exactly. So you want codes. In fact, Reed-Solomon codes can be implemented very fast in hardware, so very low energy implementations, and also all sorts of other families of codes as well. People think very hard about that. Yeah, that's a really good point. So,
the Reed-Solomon code using only for communication between 2 points, or so you can use it, for example, in a two-sided chip, for example, to see that you have a reliable computation.
So you could feasibly use it inside a chip. I think that the types of codes that are used on that scale, so for example in RAM, I know that Hamming codes are used, which is a slightly different type of code. So certainly error correction does happen at that level. I'm not sure Reed-Solomon codes are the optimal thing for that. But yeah, error correcting codes definitely are used. Anything else?
Well, then, thank you.
Thank you.